So yesterday we looked at taking the derivative at a particular point. And when we did that, we had some definition. Let me just kind of blow this up for you right now. And we saw that this was f prime. I guess I can't write on that. F prime of x naught. This is equal to, I guess I can write on that. F prime of x naught is equal to the limit as h goes to 0. And then we looked at f of x naught plus h minus f of x naught all over h. And this is where we were looking at the derivative at the point x equals x naught. We had to say that, that it was continuous there, and certain things have to happen in order to have a derivative at a particular point. And we'll talk about that in a minute. But now we're kind of just going further, and instead of just finding the derivative at one particular point, we're going to look at finding the derivative anywhere where the derivative exists on a function. Okay, so basically the derivative of a function f of x with respect to the variable x is the function f prime, whose value at x is the following. So we're going to denote it, instead of f prime of x naught, we're going to denote that it's f prime of x. So almost identical, except before the x naught, we plugged in that number. We were looking at where the derivative was at. Sometimes it's nice to be able to find the derivative of the whole function and then find particular values of the derivative. Okay, so we use the notation f of x in the definition rather than f of x sub naught as before, to emphasize that f prime is a function of an independent variable x with respect to which the derivative of the function f prime of x is being defined. We'll say that the domain of f prime of x is a set of all points in the domain of f for, and that got cut off. Okay, so the domain of f prime of x is a set of all points in the domain of f where x is defined, or where x is differentiable. There's so many ways to notate that you're taking the derivative of a function. And so you just have to be aware of all the different ways that you can write the derivative of a function. And so one of them is f prime of x, like we just were using. If we called it y, maybe we say y prime of x. dy over dx, we'll be using this sometimes for sure when we're looking at the chain rule or implicit differentiation later on in the course. df over dx, we have d over dx f of x, or we have capital D parentheses f parentheses x, or capital D with a subscript x f of x. So just be careful, because when we say d over dx or d dx, or that capital D, we're talking about operations of a function, and we're not saying that is a fraction. Here, when you see this dy over dx, this reads the derivative of y with respect to x. And if you saw df over dx or d over dx of f of x, another way to say this is the derivative of f with respect to x. Okay, so it's just two different mathematicians that came up with this One of them was Newton, and Newton does the prime. I prefer the prime, but there are some instances where the other mathematician, Leibniz, his notation was this dy over dx or d over dx. So if we were going to take the derivative at a particular value, like we did in that last section, and we wrote f prime of the number we were taking the derivative of, well, if you're using Leibniz notation, in order to notate that you're taking the derivative at a particular x value, you would write that bar there, and then x equals a, or df dx with that bar. So this is saying the derivative of f with respect to x at x equals a. So they're all just the same thing, or same thing, just written different ways. Okay. So here's just a different example of where you might see the difference. So f prime of 4. Let's say that f of x was equal to, oops, it doesn't say here, but f of x is equal to the square root of x. So one way to say this is f prime of 4, or we can say d dx of square root of x. So this basically defines what my function is with that vertical line, x equals 4. Once you take the derivative, and we can do that, you'll find that the derivative of f of x is 1 over 2 square roots of x. And if we go back in here and plug in 4, wherever we see the x, we get what the derivative is at x equals 4 for the function square root of x. Okay, so actually let's use the definition of derivative to find the derivative of that function or a rational function. All of what I'm just put here is just pieces of the textbook. So you can find that if you go to 3.2 in your textbook. And I just copied and pasted it. That way we could do more examples and you didn't have to spend a lot of time just writing some of the same stuff down. Okay, so let's say that we have f of x is equal to I'm going to do a little bit different. Sorry, I should have pulled this before. How about 1 plus the square root of 4 minus x, part A. Let's find f prime of x. Okay, so to find the derivative, we're looking at that limit as h is approaching 0. Of this f of x plus h, I'm just going to write it real quick again, minus f of x all over h. So if we plug in our pieces, so we're going to plug in x plus h wherever we see an x in this function. And so I have 1 plus the square root of 4 minus, I need parentheses around where I'm plugging in x. So x plus h in that parentheses. So that was just the f of x plus h piece. And then we have minus that whole function of f of x. So that would be 1 plus the square root of 4 minus x. And then it tells us to put the whole thing over h. If you want, we can simplify a little bit right now. Let's actually do that. So if we distribute this negative, I'm going to pull down my limit over here. So the limit as h is going to 0 of 1 plus the square root. Actually, I'm also going to distribute my negative down here, or inside that radical. So this gives me 4 minus x minus h. And distributing that negative here, we get minus 1 minus the square root of 4 minus x all over h. So things start to cancel. This positive 1 here and this negative 1 cancel. If we go in here and we go and plug in 0 wherever we see an h, notice that we'll get 4 minus x underneath the radical when h is 0. And then we would have minus this radical 4 minus x all over h, which is 0. So we're getting that 0 over 0 form, which doesn't tell us anything, which means we have to go back and manipulate this. Okay, so with radicals, the way to manipulate it is to multiply by the conjugate of where the radicals are. So right here, if I rewrote this, this is the square root of 4 minus x minus h. And then I had a minus out front minus the square root of 4 minus x all over h. So let's multiply it by that fancy 1. And the conjugate would be the square root of 4 minus x minus h plus, and the square root of 4 minus x all over, same thing, 4 minus x minus h plus square root of 4 minus x. So the whole point of doing that was so that we have a difference of squares there, and we can just square the first term or first grouping minus the square of the second grouping. So if we square this 4 minus x minus h, that radical is going to go away, minus, and then we square the 4 minus x, that square root, all over. So we're going to keep this piece in factored form. And if we didn't, then we would have to refactor it so that things cancel out later. So I'm just going to rewrite this as h all times the square root of 4 minus x minus h, and then plus the square root of 4 minus x. So things should start cleaning up. Squaring the square root again just leaves us with the radicand, 4 minus x minus h. minus, be careful because we're squaring the square root and there's more than one term under that radical. So we need parentheses around that 4 minus x. All over h all times 4 minus x minus h, that square root plus the square root of 4 minus x. So I see right away when I distribute that negative, that 4, now it's a minus 4. Those things are going to cancel. And I see this is a negative x, and when I distribute the negative to the negative x here, that's a positive x, so that's going to cancel. So we just technically have limit h goes to 0, and I notice my h is going to cancel too. I have a negative h on top, all over the h on the bottom, times that square root of 4 minus x minus h, plus the square root of 4 minus x. So now when h goes to 0, I have a number in my numerator. And so I have negative 1 in my numerator. All over the square root of 4 minus x plus the square root of 4 minus x. These square roots are like terms. They have the same thing underneath the radicals, and they have the same index, so we can add those. And so we just found that the derivative of f of x, f prime of x, this is equal to negative 1 all over 2 square roots of 4 minus x. So now, if they asked us to find the derivative at any value which is defined for a function, we can plug that value in for x. So for instance, if they said, find an equation of the tangent line at the indicated point on the graph of the function. So part B, find the equation of the tangent line when x is equal to 3. Of f of x equal to, so let me just rewrite what it was. That was 1 plus the square root of 4 minus x. Two things we need for our equation of a line, and we're trying to find an equation of the tangent line. So we need a slope at our x value, and we need a point at that x value. And so we need to figure out what f of 3 is. And that would be a point that's on our equation f of x, but it's also a point that is on the tangent line. So if we go back into our original function and we plug in 3 wherever we see an x, we get 1 plus the square root of 4 minus x, which is 3. So we get 1 plus the square root, 4 minus 3 is 1. Square root of 1 is 1. So 1 plus 1 is 2. So a point on the tangent line. is x is 3, y is 2. And now we need the slope of the line. So we can find f prime of 3. And that would give us the slope with the tangent line. Okay, so we're just going to go into the derivative function now. And now wherever we see an x, we're going to plug in 3. So f prime of 3 is equal to -1 all over 2 square root of 4 minus 3. So f prime of 3, this is equal to 1 all over 2 times the square root of 1, but square root of 1 is 1. So this would equal, oops, and I need my negative. So -1 all over 2, or -1/2. And this is the slope of the tangent line. At x equals 3. So whatever method you want to use, your point slope formula or your slope intercept formula to find that equation of the line. I'm just going to be consistent and I'm just going to use the y equals mx plus b. And how I've been doing it. So we're going to go back in, we're going to plug in our slope. We're going to plug in our point. Oops, I guess I didn't use different colors. I'm going to plug in our point. So this is our x value. Our slope was 3. Actually, our slope is not 3. Our slope is -1/2. Plus b, and our y value is 2 in this case. So if we solve for b, we know what our equation of the line will be. So 2 equals -3/2 plus b. Add 3/2 to both sides. So 2 plus 3/2 is equal to b. Let's get a common denominator. So I really have 6/2 plus 3/2. I'm not 6/2. I really have 4/2 plus 3/2, which is 5/2, is equal to b. Okay, so y is equal to our slope, which was -1/2 times x plus b. And we just found that our b value is 5/2.
Mrs. Knopfsinger?
Yeah.
Would that be 7/2?
Yes, it is. 2 times 2 is 4. 4 plus 3 is 7. Okay, thank you for catching that right away. Okay, so we found the equation of the tangent line of the function 1 plus the square root of 4 minus x at x equals 3. And I just wanted to shrink it so you guys could see more of it all together if you wanted.
Ms. Officer, can you go back to part A real quick?
Yep. Just scroll it down.
So on that last part, when you
Mhm.
canceled out the H inside of the root, how'd you do that?
I actually did not cancel it out inside the root. I was going in here, this piece here for H, I was plugging in because H is going
Oh,
to 0,
yeah.
and so that would go away.
Okay, yeah. Okay, thank you.
You're welcome. Thank you for clarifying that, though, because that would be totally wrong math if I canceled it there. You guys got it? So this actually might be a good spot if it works out. We'll see. If not, I'll come back and do some more examples. But there is a video I thought it would be good, kind of clarification again on what's going on, what we're looking at. And we had already watched one of their videos so far in this class, and I had posted that I was going to try to watch. We're going to try to watch it. Let me see if we can find it. There we go. And I'm hoping that it kind of downloaded or kind of buffered itself, but we'll see. Okay, so this kind of gives us an idea of the background of the derivative and what we're really looking at graphically when we're doing this. And so I have the link posted on my YouTube channel, but I also have it posted on the Canvas page. I'm not going to record while I show somebody else's video though. Let me stop recording.